In this video, we're going to expand our understanding of functions and think of them in terms of relations. So we're going to look at relations and how they are related to functions. So we're going to define what relations are. We're going to show how to determine if a given relation is a function. And then we're going to find formulas of functions from their forms as relations, if that is indeed possible. Sometimes it's not. So let's talk a little bit about relations very generally before we talk about how we're going to look at relations in our class. Now we're going to talk about relations mostly in terms of relations between numbers, but we can talk about relations between any types of objects. A relation is something that describes some kind of relationships between two objects or two people or two quantities. And so I'll give you an example of a few examples about what a relation can be. And we could talk about relations between people, right? One relation between people is friendship. If you take two people, either they're friends or they're not friends. So we say that two people satisfy the friendship relation if they are friends. So if I pair myself with another person who is my friend, that pair of people, we're in a friendship relation. If not, then we're not. This one's kind of weird, but it's one that I sort of came up with. We could talk about weight as a relation between two different objects. It doesn't have to be people, it could be any objects. We say that two objects satisfy the weight relation if they are the same weight. So if we have two objects that weigh the same, that is a relationship between them. Maybe not a very important one to you, but it is a relationship. Now, if we're talking about numbers, one of the most common ones is the less than relation. And that's a relation between numbers. We say that two real numbers satisfy the less than relation if the first number is less than the second number. So 2 and 5 satisfy the less than relation, but not 5 and 2. If we reverse the order, that is not going to be the case. So I wanted to sort of talk about some common themes about all three of these relations. They seem very different, but there are some things that they have in common. First of all, it's important that we think of relations in terms of pairs. We can't just have a relation between one object, or even between necessarily three objects. What we're doing is we're taking two objects and asking ourselves, do they satisfy this relation? So the items that are related, they come in pairs. Pairs of two people for friendships, pairs of two objects for weight, and pairs of two numbers for less than. And the second thing is the order can be very important. For instance, in the less than relation, it's really important what order they come. If I say 2 is less than 5 and 5 is less than 2, that is saying two different things, even though I'm using the same two numbers. So in general, a relation is a set of ordered pairs, and now when I use the word or the phrase ordered pairs, you can see how that is going to lead us to a connection to functions. So if an ordered pair in a relation, if that's part of the relation, that means the two coordinates of the ordered pair are related to each other. If not, that means they're not in the relation. So an example, if Jojo and Joanne are friends, for instance, and we're looking at the friendship relation, then the ordered pair Jojo, Joanne is an ordered pair that is part of the friends relation. Now, friendship relation, that's an important relation in real life, but in terms of our class, a more important relation for us is going to be the relation of being a function. So if we have a function f, we can think of f as relation, where xy, the ordered pair xy is in the relation if y is equal to f of x, right? We're thinking of the x coordinate as the input, the y coordinate the output, and if those two match up, then that ordered pair xy is part of our relation that is our function. So back in the old days, and this goes back all the videos that we've seen so far, whenever we expressed a function as ordered pairs or even as a table, we were looking at that function as a relation and importantly as a graph. Whenever we had a graph of a function, that was thinking of our function as a relation. So, what are some different ways that we can express or define a relation? Well, in a lot of the same ways that we used to express functions. So, we could do things like listing all the ordered pairs. So if you had a relation that just had 4 ordered pairs, for instance, like we have here, we could just literally just list those ordered pairs. So 2 and 5 are related, 3 and 6 are related, 4 and 10 are related, 3 and 7 are related. That's our relation. Now some relations have too many ordered pairs for us to list, and so we have to find different ways of expressing them. So just like we did with functions, we can give a rule. So for instance, here's a relation, x squared plus y squared equals 4. And what that rule tells us is if I have an ordered pair, and if I want to know if it's part of the relation, I square the x coordinate, I square the y coordinate, I add them up, see if they add up to 4. If they do, then they're part of the relation. So for instance, if I look at the ordered pair square root of 2 comma square root of 2, that's actually going to be an ordered pair in the relation. And the way I can show you that is true is by squaring the x coordinate and squaring the y coordinate and adding them. So that gives me square root of 2 squared plus square root of 2 squared. And when I simplify that, I get 2 plus 2, which is equal to 4. Since they satisfy that equation, square root of 2 is an ordered pair in our relation. We can also draw a graph. So if I'm looking at that x squared plus y squared equals 4, one way of drawing the graph, and you may have actually seen this graph before, it's actually a circle, radius 2, that is centered around the origin. Right, so all those points on that red graph, that is, those are the points, those are the ordered pairs that are part of our relation. So what we've seen is that some relations are functions. It's unclear whether all relations are functions. It's really natural to ask the question, if I have some random relation, is that a function or is it not a function, and how do I tell? Well, let's think about how a relation or a function as a relation works. The x coordinate of our ordered pair is the input. The y coordinate is the output, and so we got to think about how those relationships are going to work in a function. Now remember, the rule of a function is if we have the same input and we put it in twice into our function, we should get the same output. We should never have a situation where we put an input in once and get one output, put the same input in again and get another output. That should never happen. Right? So every input has exactly one output. So it is okay, by the way, for an output to have two different inputs. So you can have one input that gives you an output, another different input that gives you the same output. That is okay, but not the other way around. So here's an example of a relation. This is a perfectly good relation. We just sort of list 4 ordered pairs that tell us what numbers are related. Question is this going to be a function? Well, let's look at some examples to see if we can sort of explore what that might entail. So if I want to find, say, r of 3, now here 3 is the input, r of 3 is the output. One of the things we look at is, okay, so 3 is the input, that's our x coordinate. Let's look for an ordered pair that has 3 as the x coordinate. So that first one we see is 3, 6. And since we get the ordered pair 3, 6, that tells us that r of 3 is equal to 6. That's our rule for using ordered pairs to be functions. However, you might also notice there's another ordered pair a couple down, 3, 7, that says that, well, since the x coordinate is 3 and the y coordinate is 7, that says r of 3 is equal to 7. And now we're in a troublesome situation, right? On the one hand, we say r of 3 equals 6. We put in 3 one time and get 6. We put in 3 another time and get 7. Which is it? It's not well defined, so this isn't a function, right? So this fails the consistency requirement of being a function, which says that this relation, which, by the way, perfectly good relation, happens not to be a function. So let's look at a different relation and see if it's a function. So this is our circle, x squared plus y squared equals 4. Let's see if we can figure out whether or not it's a function. Well, here's what our graph looks like. Again, it's a circle of radius 2 centered around the origin. And let's see what happens when we plug in, I don't know, say x equals 1 into our function. What is f of 1 going to be? Well, if I want to know what f of 1 is, I've got to find an ordered pair on the circle that has x coordinate equal to 1. So I'm going to look at, see that little black vertical line? That's where x is equal to 1. And you notice that at x equals 1, we intersect the graph in 2 places, right? One at, well, x equals 1, y equals approximately, 1.732. And then on the other side of the graph, we get x equals 1, y equals negative 1.732. And of course, that's trouble, right? Because that tells us that if I want to find the output when the input is x equals 1, I have two possibilities. One is 1.732, one is negative 1.732. Again, not a function because we've put in the same input twice, got two different outputs. Can't do that with a function. Here's another example of a relation. Again, we're looking at all points where when we multiply the x coordinate by 2 and the y coordinate by 3 and add those together, we get 4. Now, if we look at the graph, we don't have the same issues that we had with the circle where we put in an x coordinate and get two different possible y coordinates, two different possible outputs. And so that means it looks like a function. But the question is, how could we prove that? How could we justify that this is actually a function? Well, one way we can do it is we can do it algebraically. Remember, y is the output if we're thinking of this as a function, x is the input, so we can solve for y to get a formula for our outputs in terms of our input. So we take our 2x plus 3y equals 4. We subtract 2x from both sides to get 3y equals 4 minus 2x. And then if we divide by 3, we get y equals 4 minus 2x plus 3, or divided by 3, excuse me. And that what that tells us is if we have an input x, in order to find the output y, we just have to multiply that x by 2, subtract that quantity from 4, and then take that quantity and divide it by 3, and that will always give us that same output. So it turns out this particular relation is a function where the formula for the function is given by f of x equals 4 minus 2x all divided by 3. So that brings to mind, why couldn't we just use this same technique when we were working with x squared plus y squared equals 4? Why couldn't we just solve for y and get a formula for that function? We know we can't because we know it's not a function. Let's see why that happens. Well, if we try to do that, we would subtract x squared from both sides, and then we'd have to take the square root of both sides to solve for y. But remember, when you take a square root, there are two possibilities for a number that can square to give you y squared. You can get, when you take the square root of both sides, you can get y equals square root of 4 minus x squared. But you also can get y equals negative square root of 4 minus x squared. And that tells you that every time you put in an input x, you get two possible outputs for y. The two possible outputs are either the positive square root of 4 minus x squared or the negative square root of 4 minus x squared, which we actually saw when we were looking at the example earlier on for x equals 1. So that tells us, since we can't solve uniquely for y, that tells us that x squared plus y squared equals 4, while it's a perfectly good relation, is not a function. Alright, so now it looks like you're ready to work on the activities. The name of the file that you're looking for is called Functions and Relations. That's you can find that right next to the PDF file that's included with this video.